For thousands of years, humans looked up at the night sky and asked a single, terrifying question. Are we alone? Until roughly 30 years ago, the only planets we knew of for certain were the ones orbiting our own sun. We had no proof, not a single shred of evidence that other stars had worlds of their own. But then, the floodgates opened. Today, we have confirmed the existence of over 5,600 exoplanets. We know now that the galaxy is teeming with worlds. But here's the twist. Most of them are nothing like Earth. We have found worlds where it rains glass, worlds made of diamond, and worlds so dark they eat 99% of the light that hits them. We are living in the golden age of discovery. We aren't just counting planets anymore. We are beginning to read their atmospheres and taste their air. We are standing on the precipice of answering that ancient question. But to understand where we are going, you have to understand the impossible things we've already found. And trust me, reality is much stranger than science fiction. Finding an exoplanet is like trying to spot a firefly buzzing next to a lighthouse from 1,000 miles away. The glare of the star usually washes everything else out. So how do we do it? Primarily, we use the transit method. Imagine a planet crossing in front of its star. It blocks a tiny fraction of light. Telescopes like Kepler, TESS, and now the James Webb Space Telescope stare at stars for days, waiting for that microscopic dip in brightness. Then there is the wobble method. Planets have gravity, and they tug on their host stars. As a planet orbits, it makes the star wobble slightly back and forth. By measuring changes in the color of the starlight, the Doppler shift, we can detect that wobble and calculate the planet's mass. In the 90s, we found the first ones. They were huge, gas giants orbiting incredibly close to their stars. We called them hot Jupiters. They broke all our models of how solar systems form. We thought our solar system was the standard. It turns out we might be the weird ones. But detecting a planet is just the boring part. The real magic happens when we figure out what the weather is like. And some of these weather reports are straight out of a nightmare. Let's take a trip to HD 189733b. From a distance, it looks like a beautiful deep blue marble, much like Earth. But do not be fooled. That blue isn't water. The winds on this planet blow at 5,400 miles per hour. That is 7 times the speed of sound. And the blue color comes from silicate particles in the atmosphere. Because of the heat and pressure, it literally rains liquid glass. And because of the winds, the glass rains sideways. If you stood on the surface, you would be shredded instantly. If that's not intense enough, look at WASP 76b. This planet is tidally locked, meaning one side always faces its star, roasting at 2,400 degrees Celsius. It is so hot that molecules separate into atoms. Iron evaporates into a gas on the day side, drifts to the cooler night side, condenses, and falls from the sky as molten iron rain. But there are worlds even stranger than raining iron. Consider TRES-2b. This gas giant is darker than the blackest coal, reflecting less than 1% of the light that hits it. If you were flying past it, you wouldn't see a planet. You would see a void, a hole in the universe, glowing faintly red like a dying ember. On the complete opposite end of the spectrum, we recently identified LTT 9779b. This is the mirror planet. It is covered in metallic clouds made of silicate and titanium. It acts like a giant mirror in space, reflecting 80% of the starlight. It's a stunning, shiny jewel, but don't look too close. The air is literally vaporized metal. Then there is the celebrity of the exoplanet world, 55 Cancri e, often called the Diamond Planet. It orbits so close to its star that its year lasts only 18 hours. While theories suggest it may have a diamond core due to high carbon content, the surface is pure hell, a global ocean of lava bubbling at nearly 2,000 degrees Celsius. If it is made of diamond, it's a diamond slowly melting in a cosmic furnace. Finally, we have the rogue planet. These are the orphans of the galaxy. worlds that were kicked out of their solar systems by gravitational chaos. They wander the frozen darkness of interstellar space, completely alone, with no sun to warm them. Astronomers estimate there could be billions of these wandering ghosts in the Milky Way, drifting silently between the stars. But while raining iron and wandering ghosts are fascinating, they aren't what keeps astronomers awake at night. We are looking for something specific. We are looking for a mirror. We're looking for a world where liquid water can exist on the surface. And recently, we found the system that changed the odds forever. Enter the TRAPPIST-1 system. Located just 40 light-years away, this is a red dwarf star orbited by not one, not two, but 7 Earth-sized rocky planets. 3 of them are squarely inside the Goldilocks zone, the habitable zone, where it's not too hot and not too cold for liquid water. It's the most promising target we have ever found. If you stood on the surface of TRAPPIST-1e, the other planets would appear huge in the sky, twice the size of our moon, passing overhead in a cosmic dance. But we need a reality check. TRAPPIST-1 is a red dwarf star. Unlike our sun, red dwarfs are volatile. They often blast out massive stellar flares, bursts of radiation thousands of times stronger than anything our sun produces. There's a real fear that these flares might have stripped the atmospheres off the TRAPPIST planets billions of years ago, leaving them as barren, irradiated rocks. We see this same risk closer to home with Proxima Centauri b. This planet orbits the closest star to our solar system, just 4.2 light-years away, and sits in the habitable zone. If we ever develop interstellar travel, this will be our first stop. But like TRAPPIST, it orbits a volatile red dwarf. The question remains, can life survive the radiation? Or does it find a way to adapt, perhaps hiding deep underground or under protective oceans? This is where the James Webb Space Telescope comes in. It uses transmission spectroscopy to analyze starlight filtering through a planet's atmosphere. It hunts for biosignatures, fingerprints of life like oxygen, methane, and carbon dioxide mixed in ways only life can produce. Just recently, JWST turned its eye to a planet called K2-18b. It found carbon dioxide and methane, suggesting it might be a Haystack world, a planet with hydrogen-rich atmosphere and a global water ocean. But a faint signal in the data caused a massive stir. The telescope picked up a tentative hint of a molecule called dimethyl sulfide. On Earth, this molecule is only produced by life, specifically by marine phytoplankton. Now, pause. This is not confirmation of aliens. The signal is weak and needs verification. Scientists are still debating if it's just noise, but the fact that we can even detect these molecules from 120 light-years away proves that we now have the technology to find life. We are no longer limited by our tools. We are only limited by time. However, finding a planet capable of life is one thing. Finding a civilization is something else. This brings us to the Fermi paradox. If there are billions of Earth-like planets and the universe is billions of years old, why haven't we heard anything? Where is everyone? Maybe life is rare. Maybe civilizations destroy themselves before they can travel the stars. Or maybe we just haven't been looking long enough. But the search is shifting gears. We aren't just looking for biology anymore. We are beginning to look for technosignatures. Biosignatures are things like oxygen, stuff bacteria make. Technosignatures are signs of industry. We're talking about finding pollutants like CFCs in an alien atmosphere, or detecting artificial light on the night side of a planet. Some astronomers are even scanning for megastructures, massive solar arrays that advanced civilizations might build to harvest energy from their stars. To do this, we need bigger eyes. NASA is planning the successor to Webb, the Habitable Worlds Observatory. Its sole purpose will be to directly image Earth-like planets around Sun-like stars. How will it do this? By using a star shade. Picture a giant flower-shaped shield tens of meters across, flying thousands of miles in front of the telescope. It's like using your hand to block the sun so you can see a plane in the sky, but on a cosmic scale. With this, we will move from guessing to knowing. We will take family portraits of other solar systems. We will see the pale blue dots, the rusty red deserts, and the cloudy white marbles. We are the first generation of humans who actually have the map. We know where to look. We have the tools. The universe is no longer just points of light. It is a landscape of places. Places with clouds, oceans, sunsets, and perhaps eyes looking back at us. Arthur C. Clarke once said, "Two possibilities exist. Either we are alone in the universe, or we are not. Both are equally terrifying." As we discover more exoplanets, the Earth seems both less unique and more precious. We haven't found a planet B yet. For now, this is all we have. But the search continues, night after night, spectrum after spectrum. Because somewhere out there, in the dark, the answer is waiting.